Namaste and welcome to the course of Elements of Mechanical Engineering. In today's video, an attempt is made to understand what is this hydraulic turbines and one such as a Pelton wheel turbine. Done? Okay. Namaste and welcome to the course of Elements of Mechanical Engineering. In this video, an attempt is made to understand what is this hydraulic turbines, what all the types of hydraulic turbines we do have, and one such Pelton wheel turbine. Okay, let's start. Hydraulic turbine, name says hydraulic, water. Water source is used to develop the electricity. Done? So this is a water source, right? And I call somewhere this is a nozzle, wherein the pressure enters with high pressure. The water enters into this nozzle. As it come out of this tip, right? As it come out of this tip, the pressure decreases and velocity increases, developing kinetic energy, and that kinetic energy rotates this wheel. As this wheel is being connected to a turbine, the power generates, and excess amount of water is flown out. We call this as a draft tube. Okay, it's just a simple explanation where I want to take you through like how this turbine works, how this hydraulic turbine actually works. I do have a nozzle, pressure decreases at this nozzle, velocity increases. I know that velocity is the one concerned with a kinetic energy that runs the system, and as the system is being connected to a generator, there the power is being generated. Done? Done there. Okay. So this is how the principle works like. The classification of water turbines, how these turbines have been classified. First is, it means classified with a type of energy available at the inlet of a turbine. At the inlet, as I said that. At the inlet of a turbine, what is the energy is being generated, that's how the classification has been done. So if say that at the inlet of a turbine, one would be an impulse turbine. So this is the energy at the inlet of a turbine, which is in form of kinetic energy. If I say this, you can say this, it's an inside the turbine, where I do have an energy. As you can see, that it is a nozzle. As I said that nozzle is the one where the high pressure fluid enters in. At this entrance exit, there won't be any more high pressure, it will be a high velocity. So this high velocity would have a kinetic energy which runs this whole system, and the power has been developed. Here, this energy has been will be developed inside the turbine. And the one at the inlet of a turbine, the kinetic energy is available. That's the energy. Okay. So another way we call such example is a Pelton wheel turbine. So another one is reaction turbine. Both the pressure and the kinetic energy both are available at the inlet. As you could see in this, the pressure somewhere outside in the reservoir, which has been pulled into this nozzle. At the nozzle, the kinetic energy at the exit of this nozzle, we have a kinetic energy, right? Pressure is outside, energy is inside. But as for concern to a reaction turbine, both the pressure and the kinetic energy are available at the inside the turbine, as you can see here. This set of blades, I do call a set of blades mounted over the turbine. One is fixed, another one is movable. One is fixed, another one is movable, another one is again fixed. Fixed where the pressure, where the water enters in, from this water enters into this nozzle and it flows over here, and we know that when it enters into this, here the pressure decreases. At this particular point, the velocity increases. That high velocity increases will be flowed over this turbine, and turbine runs. As you know that, as it comes out of this blade, still there is some energy. So again, that energy is being put into this fixed blade, where the energy still goes down. The pressure comes down here, and here at this point the velocity increases, which runs this set of blade, and then pass out. You can see this. Both the pressure and the kinetic energy are available inside the turbine. We call this as a reaction turbine. Okay, examples are Kaplan turbine and Francis turbine. Another one, it has been categorized as a head of a inlet of a turbine. Head of process from how height it has been falling through. So one is height, where the availability is more than 400 meters, which for example would be the Pelton wheel turbines, or we usually where we do have a high head. Head is more than around 400 meters. So another one is medium head, where the availability head is about 50 meters to 400 meters, in between 50 to 400. So the example is again Francis turbine. Low head turbines is the one where the head availability over there, the amount of discharge, the amount of water that we get over at the inlet of a system is around 500 meters. Then that's we said we call it as a low head turbine, and the example is Kaplan turbine. Okay. Now further, the classification is based on the direction of flow of water through the rundown. How the water will flow inside the turbine through the rundown. So this is again the classification is done. First one, tangential flow, where the water flow through the tangential of the rundown. If you could see this, the water over here is being flowed tangentially to the system, to the rundown. You can see the tangent to the rundown. So this is one type of flow where you call it as a tangential flow, right? Example, what you see over the right way is a Pelton wheel. Next is axial flow, where the water flows in a direction parallel to the axis, as you could see over here, right? So this is an axis, this is an axis of a system, right? Now water flows over here, as you could see over here, the water flows into it, right? Right, and towards the axis. Now you can see this axis. Flow to parallel to the axis. If that's happened, we call it as an axial flow turbine. Okay, example is again Kaplan turbine in this sense. Another one is based on the direction of the flow of water through the rundown. So one is radial. Again, as you can see here, radially the water has been flowing through the runner. Here the water has been flowed radially. Then if that happens, that is a radial flow turbine, where an example is a Thomson turbine, and another was mixed flow, where the water flows inside, enters in radially and leaves out axially. It enters in radially, and when it goes out axially, as you could see in this. And the example is Francis turbine. As you could see here, the water enters in radially and it flows out axially downwards. Right? So these are all the classification been done. Now to understand what is this Pelton wheel turbine. Pelton wheel turbine do consist of a penstock which has been fitted on the reservoir, where the water flows through this penstock to the nozzle. As I said very well, that nozzle is the one where the pressure at this exit of a nozzle, where the pressure will decrease and velocity will increase, where develop a kinetic energy which impinges over this wheel runs. Okay. So all the system consists of a penstock, a nozzle, a runner, and a blade and buckets all over the runner, and a casing. Right? The simple way of working is the water flow through this penstock inside this nozzle. As the water flows through this, the water will be in with a pressure energy, and the high pressure will be entering into this nozzle. At the exit of a nozzle, right? At the exit of a nozzle, the pressure decreases and velocity increases. Velocity increases, kinetic energy will be developed over there. That impinges over this bucket, and bucket starts to rotate. As this whole system is being coupled to a generator, there the power is being developed. Excess amount of water has been passed through this race. So this is how the Pelton wind turbine works. You can see the animation over here. The water flow through penstock. At this part, the velocity increases, kinetic energy has been developed, which impinges on the bucket. Bucket starts to run, has been coupled to a generator. Generator produces electricity. This is how the Pelton wheel turbine works.